Above our planet's poles, an invisible force is at work. Hypothesized decades before we were able to measure it directly, this global energy force is responsible for sculpting our atmosphere and driving charged particles into space. And in 1968, the term polar wind was coined to describe it, leading to more research and theories into its cause and effects. The idea of a planet-wide electric field was developed to explain the polar wind. But when this was theorized in the 1960s, it was thought that the force was too weak to detect. And at the time, scientists were correct. The electric potential was so weak, it would require very sensitive instruments to measure, and that technology wouldn't be invented for several more decades. Enthusiasm to measure our planet's ambipolar field was spurred again in 2016 after a clue came from the European Space Agency's Venus Express mission. One of the reasons that Earth is hospitable for life is because of its water, while Venus today is dry and barren. However, billions of years ago, evidence suggests that Venus might have had abundant water like our own world does now. This raises the intriguing question: if Venus once had water, where did it all go? The ESA's Venus Express mission offered a potential explanation when it detected a 10-volt electric potential around Venus, at least 5 times larger than expected. This marked the first successful measurement of an electric field on any planet, including Earth. The electric field surrounding Venus could pull positively charged ions like oxygen out of the atmosphere, draining it of the essential ingredients of water, like a vacuum cleaner siphoning particles out to space. Over time, this could have played a role in draining the planet of its once abundant water. This prompted a question much closer to home. Does Earth have a similar electric field? And if so, why has our planet managed to hold onto its water? The electric potential measured around Venus was around 10 volts. For comparison, a standard car battery is 12 volts. But scientists expected our planet's electric potential to be as little as 0.3 volts, similar to a button battery you might find in a watch, and some 25 times weaker than the electric potential on Venus. It's this difference that may be a key reason why our Earth has been able to keep its water. And that's what inspired NASA's endurance team to develop a new type of scientific instrument called a photoelectron spectrometer to find Earth's weak electric field. The instrument is designed to measure the speed of electrons escaping from Earth's atmosphere as a way to reveal our planet's electric potential. Earlier, I explained thermal escape, and I mentioned that particles are able to escape from our atmosphere when they reach escape velocity. That escape velocity is a very specific, predictable speed, but this speed should be ever so slightly slowed by Earth's electric potential. And so, by measuring that slowing effect at apogee, or the furthest point in Endurance's orbit from Earth, the instrument would be able to measure the strength of the electric potential around our planet. Such a sensitive instrument would need to be launched at precisely the right location and time in order to ensure a chance at making the observation successful. The Svalbard rocket range was selected for the job. It's the northernmost range in the world, located in Svalbard, Norway, a group of islands in the Arctic Ocean. Here, the NASA Endurance team would be able to launch the instrument on a suborbital rocket through Earth's magnetic North Pole. And on the 11th of May 2022, the team of international scientists did just that. Named after the ship that carried Ernest Shackleton's crew in their 1914 attempt to reach the South Pole and cross Antarctica, the Endurance mission launched its suborbital rocket to an altitude of 768 kilometers, collecting data over 518 of those kilometers before splashing down 19 minutes later in the Greenland Sea. During its flight, the instrument measured a change of 0.55 volts in electric potential between 250 kilometers and 768 kilometers. Space scientist Glenn Collinson, the principal investigator for NASA's Endurance mission, said even though half a volt is almost nothing, again almost about the strength of a watch battery, it's just the right amount to explain Earth's polar wind. This first ever direct measurement of Earth's electric field marked a pivotal moment in our understanding of this fundamental planet-wide energy force.
It's called the Ambipolar field, and it's an agent of chaos. It's an electrical field. It begins at about 250 kilometers above your head, and it keeps going. The atmosphere up there is different than the atmosphere down here. Thinner, right? There's less of it. So think about just one atom. Here it is. The sun shines on it, it breaks off this electron. So now we have this negatively charged electron and this positively charged ion, and the two are attracted towards each other. The electron would happily escape all by itself, but the ion still feels the big tug of gravity. So as the electron tries to pull away, the electric force forms between the two to restrain it, to keep it from escaping. And it also helps pull the ion upwards. The field works in both directions. It is ambipolar. Imagine you're walking a dog, and you've got a tiny, tiny little dog, and it's pulling on a leash. That dog's going nowhere. This ion and electron pair that you've been thinking about, they're only one in an enormous sea of the ionosphere. But overall, because gravity's pulling down on the ions, it adds up. And over a large distance, you get this field forming. It's like this conveyor belt that's countering gravity and lifting the ions up so they can escape to space, which is why it may have had an impact on the evolution of the atmosphere.